Let's take a look at an example that has a little bit of a trap in it. So we have this function x to the fourth plus 1 all over x squared, right? And initially we might speed right through it, go to the derivative, go to the critical values, right, on our way to finding when the function's increasing, decreasing, so on and so forth. But I think we always need to be cognizant when we start the problem. Is there anything suspicious, right? And what do I mean by that? Well, is there any place where this function might have some domain restrictions? And in this case, it does, right? So we have a situation here we need to be mindful of. Right away, we realize x cannot equal 0, and that's going to come up a little bit later, so hang tight for a minute. Let's go about it like we normally would, right? We need to find the derivative. So you have options. You could do the quotient rule if you like. I personally like rewriting it. I like putting x to the fourth over x squared, also plus 1 over x squared, and then rewriting that, make it cleaner, just a little quicker. So as x squared plus x to the negative second, right? That is so much easier to derive in my opinion. So let's go do that. First derivative, 2x minus 2x to the negative third, right? Now we know we're going to need to find critical values. We need to test those values. I don't know that this is the most user-friendly way to look at this, right? So in my opinion, what I might do here is I might factor a common factor of 2 and an x to the negative third out of there, right? So that gives me 2x to the negative third. What does that leave me with right here? Well, that would be x squared, right, minus 1. A little easier now to see what might happen in terms of critical values. So one more time, let's just write a little cleaner here. X squared minus 1, right, all over x cubed. Okay, so where are my critical values? Well, again, where the derivative is 0, so that would be where the numerator is 0, right? So that would have to be plus or minus 1. Or where the derivative is undefined, right? So that would have to be where the denominator is equal to 0, and that would of course be 0, which makes sense also because, look, we had a restriction in the beginning. So again, we'll get back to that. So let's test, right? Here we go, number line. Here's negative 1, here's 0, here's 1. And so everything looks, pretty status quo, I would say. The one thing I might recommend is that maybe you just put a little bit of a box around 0. Why? Because that was a restricted value, right? And so we don't want to make conclusions about what's happening here at 0 if they're really not true. And I'll explain what I mean by that. So as we test, right, we pick a number bigger than 1, we substitute it back into the original problem, let's say 10, right? Okay, positive here, positive there. Derivative overall is positive, so f is increasing here. Okay. Take something like a half, right? 1/2 squared is a fourth. 1/4 minus 1, that's a negative number up top. That's going to be positive, so overall, we have a negative derivative here. Function's decreasing. We continue on, right? Try negative 1/2, right? Again, we're going to get a negative up top, but we're going to get a negative on the bottom as well. Derivative winds up being positive, function increasing. Okay, and then lastly, again, use something big, negative 100, right? Positive, positive. I'm sorry, negative 10, right? Positive here, negative on the bottom. So now we have f decreasing. So again, kind of on the surface, it looks pretty normal, right? Nothing crazy going on. And that is true for the most part. So we can make a reasonable conclusion that f is increasing from negative 1 to 0, right? And again, from 1 to infinity. F is decreasing, negative infinity to negative 1. And again from 0 to 1. Okay, so again, all reasonable things. Here's where we get a little stuck, or we run into a little trouble if we're not paying attention. Where are the extrema? Well, function goes from decreasing to increasing at negative 1 and again at 1. So we have a relative min, right, at both x equals plus and minus 1. All right. However, and this is where you have to be careful, we see the function is going up until 0 and down after 0. Problem is, we can't call that a relative max, because if we do, that means that there will be a point, a maximum point on the graph of f of x, and we know that can't be true since there's an asymptote there. So we have no relative maximum in this function. Again, a great example to maybe just verify graphically. Thanks for watching.